Okay, so this is the discussion of Chem 113, Exam 2. So we'll be going through each of the exam questions and talking about key concepts. So in the first case, we're looking at question 1, which discusses the HWE or Horner-Wadsworth-Emmons reaction, which uses a modified stabilized ylide to prepare alkenes with really great stereo control. So in this case, we're asked to predict the major and minor product from the reaction, draw a mechanism, and draw a Newman projection clearly showing how the major and minor product are produced. Okay, so the first thing to note is because we have a stabilized ylide, we'd expect to see a strong preference for the E-alkene generated. We're expecting the E-alkene to be major, while the Z-alkene is minor. So in terms of the mechanism for this reaction, first we have attack of our ylide onto the electrophilic aldehyde carbonyl carbon. And we're going to draw the mechanism first for the major product pathway. From here, after addition, we get the following addition product. I'm going to draw this like so, just to help emphasize that this phosphorus is highly electron deficient. Now, when we have a stabilized ylide, the E-alkene product is favored in most cases. So in terms of the Newman projection for our addition product, for the major product, it looks something like this. After rotation, so that our phosphorus is adjacent and close enough to the oxygen atom to form our cyclic four-membered betaine intermediate. Let's pay attention to how our other substituents are arranged. So when we line up our electrophilic phosphorus atom and our nucleophilic alkoxide ion generated, we see that after rotation, we can see very clearly that our bulkiest substituents are on opposite sides of our alkene in the Newman projection. After we form our phosphorus-oxygen bond and make this betaine intermediate, This betaine intermediate collapses via a retro 2+2 reaction, and that gives us our corresponding E alkene. This is our major product from this Horner-Wadsworth-Emmons olefination reaction, which resembles and is identical mechanistically to the Wittig reaction when you have a stabilized ylide. Any questions on the mechanism and the Newman projections drawn for this reaction? Any questions on this reaction? So if we're looking at the minor product and the pathway for the minor product, after addition for the minor product pathway, we observe the following Newman projection. And it's a subtle difference, but it's an important difference to note. In this case, after rotation, we see quite clearly that our bulky substituents are on the same side of the alkene. Just making sure I'm drawing things properly after rotation. So again, we get this betaine intermediate. And then this betaine intermediate collapses to give us the Z alkene, which is minor. Does this mechanism make sense to everyone? Any questions on this problem? Okay, so let's keep going and let's look at the next example. In this case, we're asked to predict the product of the following reactions and draw a mechanism for each reaction. So we see the thiourea method used in route A. And route A, or the thiourea method, is great for asymmetrical sulfides, while route B utilizes sodium hydrogen sulfide, which is great for symmetrical sulfides. So with that in mind, if we look at these two compounds and we're asked which of these synthetic routes is most appropriate to prepare these compounds, as we can see, the first compound is asymmetrical. So method A, or the thiourea method, is most useful to prepare this asymmetrical sulfide. Conversely, this symmetrical sulfide with two identical alkyl groups is best prepared from the alkyl sodium hydrogen sulfide. Does that initial discussion make sense to everyone? The uses of the thiourea method versus the sodium hydrogen sulfide method. The thiourea method is most useful to prepare asymmetrical sulfides. Okay, so let's now talk about the mechanisms for each of these reactions and predicting the products from each of these reactions. So in the first case, we have thiourea and a typical alkyl halide. Mechanistically, thiourea will attack and displace this alkyl halide via textbook SN2 reaction. So we formed a carbon sulfur bond. And now, because we have a base present in solution, triethylamine will just pull off a proton from this aminium-like species and give us our neutral SN2 displacement product. Does this mechanism make sense to everyone so far? Does everyone see how we get the product from this first step? We've talked about the thiourea previously in, I believe, the chapter 18 note set for the thiourea method to prepare asymmetrical sulfides. So from here, treating this thiourea species with sodium hydroxide frees up our sulfide. So in the first case, hydroxide will attack this electrophilic imine-like carbon. That in turn gives us a tetrahedral intermediate. From here, we can kick down our lone pair and free up our sulfide. So in this case, we lose our thiol as a leaving group. That in turn gives us this thiol-derived anion, which can then react with common nucleophiles, in this case, this cyclohexyl chloride. From here, this forms another carbon-sulfur bond, and this gives us our desired asymmetrical sulfide product. Does this mechanism make sense to everyone? Any questions on this example? Okay, let's look at the mechanism for the hydrogen sulfide process. In this case, when you have an alkyl halide and you treat it with sodium hydrogen sulfide, rather than seeing simple monoalkylation, you typically end up getting polyalkylation. And this is why sodium hydrogen sulfide is useful for generating symmetrical sulfide products. So in this case, our first step for this mechanism is our sulfur nucleophile will attack and displace our chloride leaving group via a typical SN2 reaction. However, this reaction doesn't stop there. We still have some alkyl halide floating around, And so our sulfur nucleophile will attack a second equivalent of alkyl halide, giving us the symmetrical sulfide product. From here, we can deprotonate with triethylamine, and that gives us our neutral, isolable, symmetrical sulfide product. Does that make sense to everyone? Okay, so we've drawn the mechanism for each of these two reactions. We've predicted the product for each of the reactions, and we've discussed how each of these methods can be used to prepare symmetrical and asymmetrical sulfides. Okay, let's keep going then. In this case, we're asked to propose a synthesis of the following molecule. Now, there are two ways to break our carbon-oxygen bond if we wanted to prepare this compound via the Williamson ether synthesis. There are two options, A or B. For route B, if you try to use this butanol-derived nucleophile and you react it with tert-butyl chloride, you would not see an efficient reaction because this is a tertiary alkyl halide. So this route doesn't work. You'd primarily see elimination when you have tertiary halides. Instead, we're going to break bond A and trace this back to chlorobutane and tert butoxide. From here, we have just a textbook SN2 reaction, and that gives us our desired ether product. So this is the classic Williamson ether synthesis. Does this example make sense to everyone? Are there any questions on this example before we move on? Okay, so let's keep going then. In this case, we're asked to predict the product from each step in the reaction sequence and draw a mechanism. So in the first case, we have phenol, or this phenol derivative, reacting with allyl chloride. So this is a textbook SN2 reaction occurring through an SN1 mechanism because it is allylic. From here, in this case, a second equivalent of our substrate can go in and pull off the proton. From here, this gives us an allyl ether. And if we heat this allyl ether, as we discussed in chapters on aromatic systems and pericyclic reactions, under thermal conditions, we have the correct arrangement for a 3-3 rearrangement or a Claisen rearrangement. This gives us the corresponding alpha allyl ketone product. However, this product does not stick around for very long in solution. In this case, we can lose a proton and protonate our carbonyl oxygen, and that tautomerizes our ketone to the more stable aromatic enol form in this case. Does this mechanism for each step in the reaction sequence make sense to everyone? Any questions on this example? Okay, let's keep going then. In this case, we're asked to predict the product from each step in the reaction sequence and draw a mechanism. In this case, we have an alkyl halide reacting with a nucleophile, in this case, cyanide. So our nucleophile will attack and displace our primary alkyl halide via a textbook SN2 reaction. And that gives us the corresponding nitrile. From here, when we treat this substrate with acid, something pretty interesting happens. One common thing I noticed, just that I'd really like the class to note, please make sure that you're counting your carbons correctly, so your structures don't have more or less carbons than required. I noticed sometimes they drew the nitrile and deleted a carbon. So when we treat a nitrile with aqueous acidic conditions, we're first going to protonate the nitrile. From here, a new internal nucleophile, such as this alcohol, can attack our nitrile. And this is one thing that's pretty unique about this example. Because if we think about the rates of reaction, an intramolecular reaction is going to be substantially faster than the intermolecular reaction, correct? As such, it's far more likely for the internal alcohol to attack than an external alcohol. Does that argument make sense to everyone? From here, we're going to see a series of proton transfers where our imine-like nitrogen is protonated. And where we deprotonate our alcohol oxygen. So now that we have this activated iminium-like species, water will attack and generate another tetrahedral intermediate. From here, we're going to do a series of proton transfers to free up a lone pair on oxygen and activate our amine as a leaving group. So from here, we now have this tetrahedral intermediate primed and ready to lose our leaving group. So our tetrahedral intermediate is going to collapse. And then we're going to kick out our leaving group. From here, we just have one cleanup step to go. In which case, we're going to pull off a proton. And that gives us our lactone product. Does this example make sense? People also drew the carboxylic acid, and that's not unreasonable. So I only took off a small point for that. Technically, you'd isolate, and you'd probably be able to isolate the lactone product, preferentially over the free carboxylic acid. Does this example make sense to everyone? Any questions on this example before we move on? Okay, let's keep going then. In this case, we're asked to propose a synthesis of the following from a starting material containing a nitrile, carboxylic acid, and amide. And those certainly were creative. They weren't wrong, but I just like to highlight some more efficient synthetic routes using the methods that we've learned in this class. So first, if we want to prepare from a nitrile, we can just break bond A, and we know that nitriles can react selectively with Grignard reagents. To generate the corresponding ketone. So that's our first synthetic route down. What about a carboxylic acid? So we can trace back, and let's think about this for a moment. We can break this bond and trace back this ketone to an anhydride and an organocuprate. And of course, we can prepare this acyl chloride from the corresponding carboxylic acid. So now that we have our reverse reaction, our retrosynthesis set up, let's now draw out our forward steps. So first, we can prepare chloride using thionyl chloride. That's pretty straightforward. And then from here, we just treat it with lithium diethyl cuprate. And then quench with water. And that gives us our corresponding ethyl ketone. Does that make sense to everyone so far? Okay, let's look at our last route. In this case, we're trying to prepare a ketone from the amide. So I'm going to trace this back to addition into a nitrile. And we know that we can prepare nitriles readily from the corresponding amine. Make sure that you counted your carbons correctly so that way you don't end up with too many carbons at the end. So in this case, we're going to take our amide and we'll generate the nitrile via treatment with thionyl chloride. From here, once we have our corresponding nitrile, we'll treat it with ethyl magnesium bromide, followed by an acidic quench. And that gives us our corresponding ethyl ketone. Does this problem make sense to everyone? Okay, so let's keep going then. In this case, we're asked to predict the product from each reaction and draw a mechanism for each reaction. So we have a secondary amine, catalytic acid, and a ketone. These are textbook conditions for enamine formation. So as we're under catalytic acidic conditions, the first step is to protonate our ketone. From here, our nucleophilic amine will attack the electrophilic carbonyl carbon, and this gives us our tetrahedral intermediate. From here, we're going to engage in a series of proton transfers, activate water as a leaving group, and to free up a lone pair on our amine nitrogen. So we're going to protonate our alcohol to activate it as a leaving group, and we're going to pull off a proton from our amine to free up a lone pair. From here, now that we have water activated as a leaving group, we're ready to kick out our leaving group and generate our imine. However, this isn't a normal imine. Because our parent amine is secondary, we have an iminium ion. And this iminium ion is not stable. Now, one common error that I found, and this is something that we talked about extensively for imines that's slightly counterintuitive, is that although in many cases, yes, the most substituted alkene is generally stable for normal alkenes, in the case of imines, substitution and steric strain destabilizes your imine and affects the amount of resonance stabilization you can get for your enamine. As a result, when you form the enamine preferentially forms to generate the least substituted alkene to minimize steric hindrance and to maximize orbital overlap and resonance stabilization as a result of that delocalization of electron density. So, to make a long story short, enamines prefer to form on the least hindered position. Enamines can be thought of as a kinetic enolate equivalent. So in this case, water is going to pull off our proton. And we'll generate our enamine at the least hindered position. Now, you may say that's a pretty minor detail to obsess over. Well, this is very important because this is part of the reason why enamines are practically utilized in synthesis, because there are means to selectively prepare kinetic enolate equivalents. So does this mechanism and does the product drawn from this reaction make sense to everyone? Any questions on this example? Okay, let's keep going then. So in this case, we're asked to predict the product from this reaction and draw a mechanism for this reaction. So we have two alcohols, a ketone, and an acid catalyst. This is a textbook Acetol Formation set of conditions. Okay, so in this case, the first thing that's going to happen as we're under acidic conditions is we are going to protonate our ketone. This in turn activates our ketone for a reaction with nucleophiles. In this case, rather than having our alcohol nucleophiles be external nucleophiles, in this case we have an internal nucleophile. So our activated carbonyl carbon is going to be attacked by our alcohol in an intramolecular fashion. Remember, intramolecular reactions are orders of magnitude faster than intermolecular. 1, 2, 3, 4, 5. That in turn generates this 5-membered hemiacetal, or in this case, hemiketol, because it's ketone derived. From here, we now have to have a series of proton transfer steps, the first of which involves protonation of this alcohol to activate it as a leaving group and removal of a proton from our nucleophilic alcohol oxygen atom in order to free up a lone pair. So now that we've completed these proton transfer steps, we now have activated water as our leaving group. So we're going to kick out our leaving group. And that gives us the following activated carbonyl derivative. This activated carbonyl carbon can be readily attacked with a range of nucleophiles, such as this internal alcohol. From here, that in turn gives us this cyclic ketol, which is isolated as a neutral isolable product after deprotonation of our oxygen atom with water. This gives us our desired let me draw this a little more cleanly. This gives us our desired ketol product. Does this reaction make sense to everyone? And does this mechanism make sense? Okay, let's keep going now. In this case, we're asked to predict the product from each reaction. So we have an enone and an organocuprate reagent. These organocuprate reagents prefer to add 1,4. So in this case, we'd end up with addition of our isopropyl group at the 4 position. You can draw the enolate generated, or you can draw the neutral 1,4 addition product. Grignard reagents, by comparison, prefer to add 1,2. They are considered quote-unquote hard nucleophiles. As such, our isopropyl group adds 1,2 to the carbonyl carbon, giving us the following product. Amines and sulfides in the context of enones are considered soft nucleophiles, and they will preferentially add 1,4 rather than generate the enamine product. As such, we get the following 1,4 addition product. Any questions so far? Any questions that I can address so far on these examples? Okay, for this next example, we have a primary amine and a ketone. There are 2 acceptable answers in this case. You can show the adduct, but more likely than not, this adduct will dehydrate and generate the corresponding enamine. Any questions on these examples? Okay, let's keep going then. So in this case, we're treating the following alkyl benzene derivative with potassium permanganate and H3O+. These are textbook exhaustive benzylic oxidation conditions, in which case only the primary position is oxidized up to the corresponding carboxylic acid. In this next case, we're treating this alkene with ozone and hydrogen peroxide. This is a textbook oxidative workup. And thus we would expect, after ozonolysis of our alkene, that we would isolate the corresponding carboxylic acids. Remember, as there are free hydrogens at both sides of our alkene, we'll be able to oxidize up both of our alkene carbons to the carboxylic acid oxidation state. Any questions so far? Okay, for our last example, we're treating a nitrile with lithium aluminum hydride followed by water. This results in exhaustive oxidation of our nitrile to the corresponding amine. Make sure to count your carbons because I noticed many students ended up drawing a structure that had 1 too many or 1 too few carbons. Okay, so with that, we finished our run through of exam 2. Any questions I can address on exam 2? If we don't have any other questions, what we'll do is we'll archive